Looked at my accounts, you saw that there were problems online. I'm perfectly happy to do these problems that I've written down. I'm perfectly happy to do the problems that you want me to do out of the book or anywhere. Is there any, we could start with requests, either topic or let me know what you guys want to do. Or do you just want me to start to cranking? Go ahead. All right. The test, in my opinion, is going to be the usual 8 to 10 multiple choice. Not really sure what that's all about. My guess is that it's going to be over the chapters. You're going to have chapters 8, 9, 10, and 11. And my guess is that there will be 2 or 3 of the multiple choice on each of those. Chapter 8 is rotational motion. Chapter 9 is rotational and translational equilibrium, or dynamical equilibrium, but this is how I normally do it. Number 10 is fluids. And then 11 is simple harmonic oscillators, either the pendulum or the spring. And what I think is going to happen is the 4 problems that he's going to do are going to be one from each of these major subjects. I think that in my opinion, 9 and 11 are the easy ones, followed by 8. I don't think the difficulty of 10 is all that bad. The problem with 10 is that it's a rather large chapter. And so there are many of different classes of problems that could happen. Now what I'm going to do is I'm just going to kind of start working through these problems in the order of chapters. So I need a rotational motion one. I got this one. I got those 2. All right, so we got 3 of these. So let's just do some examples. Now, in this first one, I'll go in order of difficulty. And so these are the problems. You have a disc. The mass of the disc is 100 kilograms. The radius of the disc is 2 meters. If the force is 400 newtons, from rest, how long would it take to rotate 100 times? It's a rotational motion problem. And once again, the rules from last night apply to tonight. If you don't understand anything, let me know. If you got questions, let me know. If you think I've made a mistake, really let me know. Don't just sit there and be quiet. So for this particular type of problem, with linear motion, there's a set array of tasks that you need to do. With this, it's a little bit more nuanced. With rotational motion, the equations that are your friends, sum of the torques is I alpha. Other ones, theta equals omega naught t plus 1/2 alpha t squared. Now, for a lot of these, you're going to need to know some other equations. Since I asked about it rotating 100 times, that little guy means that you need to have the equation theta equals 2 pi n. And because I'm dealing with a force causing something to rotate faster and faster, you need to know that torque is equal to the force times its distance, or R. In this case, it's big R. Since it's a disk, the moment of inertia of a disk is 1/2 mr squared. If we need any more, we'll look for it. Now, obviously, one of the unknowns that we have, and I underline them in red, is alpha. The other thing that I don't have is time. So this particular equation is all sorts of messed up. The advantage that I have is what we do is we use the alphabet soup notation. There is one exemption, or one, I forget, I don't know English all that well. The one time that you do want to plug in a number for certain is 0, because 0 eliminates a lot of stuff, and in this case it's here. So this equation can be rewritten as 2 pi n is equal to 1/2 alpha t squared. Now this one, torque is Fr. I is 1/2 mr squared. And then we have alpha. All I'm looking for is time. And really, what I'm doing is I'm showing you how I would be teaching you in class, which is we do not plug and chug until we need to. The alpha is the unknown, and the alpha here is one of 2 unknowns, and the alpha over here is one of 1 unknown. One of those r's cancels. So I'm going to rewrite this as 2f over mr is equal to alpha. I'm going to take that and plug it in there. So 2 pi n is equal to 1/2 alpha, which is 2f over mr t squared. Now when you look at this, t is the only unknown. I'm giving you n, f, r, and you're looking for t. Okay. Those 2's cancel. Also, one thing that you never hear me say is it can be easily shown that. I'm going to show you all the gory steps in the middle. 2 pi n mr over f is equal to t squared. So t is 2 pi n mr over f. And this gives me, oh wait, now I am allowed to plug and chug. 2 pi n is 100, m of the disk is 100, r is 2, and then f is 400. Ooh, and also the other thing that I really love to do is I love to write my problems where stuff cancels out. 2 times 2 is 4, times 100 is 400. So those cancel with that. So the answer is square root of 100 pi, or 10 times the square root of pi. And it simplifies it. So had you plugged all that in together, you would get the same answer that I'm going to get, which is 17.72 seconds. So you could either plug in everything there or just simplify it to that. Either way, you'll get the same answer.
Okay, this is a dumb question. What's
N
n?
is, now n here, this 100 times is equal to n.
Okay.
Now this n here, I can understand the confusion, is Newton.
Hey, Ashley.
Yes?
So the 2 pi n is not on his equation sheet. Do you think he'll mark this off or just leave it?
I don't think he would. I think it's an entirely valid. Does he ask questions about how many times did it rotate, or then you're going to need 2 pi n is equal to theta.
Oh yeah. Would it help when we say original sheet if we give this
Yeah, now he may have just forgotten it. I don't think, I would never assume that, I mean, I would never assume any of my equation sheets had every equation.
yeah.
So,
Especially because that's what we derived. That's direct though, you know, the 2 pi.
yeah, there's some things. Did he put the definitions of sine, cosine, and tangent on it? That's just something that you should know. But, I mean, though I put it on, but it may not be something that he does. It's just, if you go one rotation, that's 2 pi radians. So every multiple of 2 pi is one rotation. So I think that's kind of...
Right.
Though I will say the one bit of advice that I gave him was, never assume that your students know anything about anything. So I think it's a valid point to put it on the sheet. I wouldn't make it that big of a deal in terms of if I was the professor. I'd throw it on there and just not care. It doesn't matter. I do think, now this is the thing that from what I understand, he's gone from one extreme to the other, where initially he had practically nothing on his equation sheet, and now he's throwing everything at you. So what the trap that you could fall in is you're spending so much time on the equation sheet that you don't really know what to do with it, and then you're just wasting time. So in my opinion, just practicing and being able to manipulate the equations because they're in your head is probably the best way to go. All right. Now, in this particular case, I have a disc with a bar slapped onto it. I want to know what the force is, and I want to know the number of rotations it made. It goes from rest to an instantaneous frequency of 50 hertz in 60 seconds. Now, in this particular case, we have to know the usual suspects of equations. That the sum of the torques is equal to I alpha. Now, because of this I is the total I, which means it's I of the disk plus the I of the bar. I think that the three basic shapes are disk, cylinder, or disk cylinder, the bar, a point. That's about it. I don't think he's going to get super exotic by using spheres or hollowed out spheres or garbage like that. I think he's going to keep it simple. The moment of inertia is 1/2 md r squared plus 1/12 m L squared. So this is now this is the one time that I do think plugging it in helps, because writing that 10 times is just going to get laborious. So this R is 3. The M of the stick is 20. And then the L is 2 times R, or 6. So this makes it to be I get 195. And 195 kilograms meters squared. Yeah. All right, got it? All right, good. Okay. So this is the moment of inertia of the system. So that I right there is 195. There's only one force, one torque. So F R is equal to I alpha. Now, I didn't ask anything about alpha. What that typically means is that I'm eventually going to solve for it or substitute it out. So FR over I is equal to alpha. The other usual suspect is theta equals omega naught T. That's 0 because it starts from rest, plus 1/2 alpha T squared. The theta is 2 pi n, where n is the number of rotations. 1/12 is the moment of inertia of a bar rotating around its center of mass. That equation is on the equation sheet. So. Now the problem hold on. Is there a problem? Let's see.
So like, the rod is like rotating through the center, right?
The rod is welded to the disc. So it's rotating about its center of mass along with the disc. In this particular case, I like to do a status check with what I know and don't know. I know R, I know I know, I don't know a lot of stuff. T, and that's it. I don't know N, I don't know alpha, I don't know alpha, and I don't know F. Well, goodness, we're just doomed. So we got two equations, each with an array of unknowns. But I gave you something else. I said that it goes from rest to frequency of 50 hertz in 60 seconds. The other equation along with this, my favorite equation is the equation of motion for position. X equals x naught plus x naught, v naught t plus 1/2 at squared. This is the linear version, or I'm sorry, the rotational version of it. The rotational version of velocity is omega equals omega naught plus alpha t. That omega naught is 0 because it's at rest. This particular equation needs another equation, and that is 2 pi f is equal to omega. So 2 pi f is equal to alpha t, or alpha is 2 pi f over t. Okay. Now in the, now this is where I'm going to need more paper. For these two equations, what I did is anything I don't understand, I underline in red. Anything I do understand, I underline in green. The equation on the left, I don't know force and alpha. The equation on the right, I have number of rotations and alpha as unknowns as well. When you're doing linear motion problems, frequently, if not always, it breaks down into two categories. It's either a two equation, two unknown, and you know how to do those, or it's a one equation only has one unknown, and you're able to solve for it, and then the rest of it. This is two equations, three unknowns, where the unknowns are f, alpha, and n. Well, there's another equation that can help you out. In linear motion, x equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. Well, their associated equations is that and that. That the initial angular velocity plus alpha t is the final angular velocity. Well, I know what the initial angular velocity, it's 0. I don't give you the angular velocity, but there is a conversion for it. The conversion is 2 pi f is equal to omega. That should be on the sheet. If not, it should be. Which means that 2 pi f is equal to alpha t. With linear motion, it's a lot like a recipe. You do step 1, 2, 3, 4, etc. With a rotational motion, it's more like a jigsaw puzzle. You have all the pieces, you just got to sit there and kind of just finesse it into fitting. In this particular case, I can solve for alpha. I can actually get a number. But since I'm a passionate believer in the alphabet soup method, I'm not. Now, if I asked for alpha, then I would, but in this case, I'm not. Well, if I know alpha, those become knowns. And now I can solve for F and I can solve for N separately. So much of this is identifying what you know and what you don't know, and then being able to substitute in other things. Now that becomes, so this equation here becomes FR over I is equal to 2 pi F over T. I'm looking for F, so F is 2 pi IF over RT. R comes down, I goes up, F is left there. So this is 2 pi 195, which I calculated there. F is 50. R is 3. T is 60. Now, this R here is the distance from the rotation point to the force. If it was on a different radius than the, or at a different distance than the radius, then it would have to change. So 2 pi and I get a force of 340.33 newtons. To get the number of rotations now is this. So number of rotations is alpha t squared over 4 pi. Alpha is 2 pi f over t. So 2 pi f over t. And then I'm left with t squared over 4 pi. One of the things that I love to do is to do it by alphabet soup mode because stuff just cancels out and substitutes there. So this just becomes ft over 2, which is 50 times 60 divided by 2, or 1,500 times. I think, unless I did the math wrong. Yep, 1,500. Yes? The 195 is the moment of inertia of this combined disk and stick. And one of the things that helps with moments of inertia is that if you have mass, if I said you have a 1 kilogram mass and a 2 kilogram mass, and I said, how much mass do you have? You would say 3. You just add them together. It's the same thing with moment of inertia. The moment of inertia total is the moment of inertia of the first one plus the moment of inertia of the second one. Now there's something a little bit more involved because it's a mass distribution, so you need to pay attention to that, but that's the overall stuff. Okay. Any other questions about this one for rotational motion? All right. Now this one, and if when I present this and you go, oh, he's never going to do that, let me know and then we can skip it and move to something else. This is a conservation of angular momentum problem. Do you think he would cover that on rotational motion? Because it is chapter 8. Yeah, check the checklist.
Yeah.
Conservation of angular momentum? Okay.
Yeah, no, I did a lot of conservation of
Okay, good. Now what this is kind of an equivalent of, you've got an ice skater, she has her hands out, and then as she's twirling around and she pulls her arms inward, she spins up. Why is that? Because she's changing her moment of inertia. She's decreasing it. And angular momentum initial must be angular momentum final. It's a lot like the conservation of linear momentum that you had in collisions. Now, what is the initial, or what is angular momentum? Well, angular momentum is the moment of inertia times omega. So you get that set up. Now, we have omega, but I gave you f. And you know that 2 pi f is equal to omega. So this is equal to I 2 pi f I equals I final 2 pi f final. And the 2 pi's cancel. So the big thing about this is to find the final frequency. To find the final frequency, we're going to have to find the ratios of moment of inertia initial divided by moment of inertia final times the final frequency. That's F sub f. Well, let's go find that. The initial moment of inertia is the moment of inertia of the disk plus 3 times the moment of inertia of the point at distance r. The moment of inertia final is the moment of inertia of the disk plus 3 times the moment of inertia of the point at r prime. This means that the disk is 1/2 mass of the disk r squared plus 3 mass of the point r squared. So this is 120, 3 squared, 3, 40. R over 3 is 1. So that is 60 times 9, or 540, plus 120. So it's 660. The moment of inertia final is the moment of inertia initial, or of the disk. So it's once again 1/2 mdr squared. But now, rather than r, we're using r prime. Oh, wait, whoa, stop. This r here is that r. The distance from the center outward, you guys aren't catching me, is that. So it's not a 1, it's a 3. So it's not 660, it is 1620. Because I felt it was a little bit light, and now I saw why. Now this one, that one is 1, because 3 divided by 3 is 1. So this is 1/2, 120, 3 squared plus 3, 40, 1 squared. And this is the 660. And now I'm double checking myself because I don't trust me. 660. Which means that the I initial is 1620, the I final is 660, the initial frequency is 1, so the final frequency is 2.45. Well, what happened initially is that the points were at the edge of the disk, and then the points moved towards the middle. such that their new radius is 1/3 that of the old radius. There's a good demonstration of kids on a merry-go-round, in a playground, and what they do is each of them move towards the center, and then the end result is it spins a lot faster, and then it slings the kids off, and that's what they call fun. It's on YouTube. It's all over the place. So, but that's the last of the rotational motion problems that I have, and so we'll move on to another one. So after 8, after 8 there's 9, which I think is kind of an easy one, but we're going to do some basics. Mm-hmm. Which equation? This one? Well, it started first from conservation of angular momentum. And then I said, well, what's angular momentum? I omega. And then what's omega? 2 pi f. And then what I needed was, in this equation here, I know these 3 and I don't know that one. So what I do is, that's the question, solve for the final frequency. And then I get II, because I divide both sides by IF, to get this. And then the real question becomes, conservation of angular momentum is all about determining the moment of inertia of the object, or objects in their various orientations. Yes? Yes. And I just know what? That's the initial. Yeah. Okay, this is a clarification on how the problem reads, because when I write test questions, I just sketch. If the initial frequency is 1 hertz, what is the new frequency? The initial position is irrelevant. What it is it's just spinning around at 1 hertz, and then the masses on the edge of the disk move inward. What is its new frequency? Because normally when I write tests, I write the notes like this, and then the next day I look at it and go, what idiot wrote the words? And then I flesh it out.
Right.
So.
Okay. Thank you.
Mm-hmm. Yes.
I understand where you got the 1/3 on the right side, because of the R prime.
Yes. Well, that's a definition. That's just what I said.
Yeah. I don't understand why you didn't put it to the left side when you solved for I initially.
Because here, the disk is of radius r, and the 3 points are at radius r. Here, the disk is at radius r, but the 3 points are at r prime. And that's the difference. That's good. All right, we are on schedule. Now, what I'm going to do first is a pure translational equilibrium problem, and that is this guy. You have a mass, a 20 kilogram mass, hanging from the ceiling. There are 2 wires, one with a tension T2, which is pulling perpendicularly to the right, another one, tension 1, which is pulling up and to the left, and an angle is given there. What are the tensions in the 2 cables? In a problem like this, translational equilibrium is your friend. In problems like this, your observation that this is doing nothing. And doing nothing, if you're just lying in bed over winter break and your mom's saying, hey, you're not doing anything, you can just say, I'm studying physics, I'm in translational equilibrium. Because at this point, you can say for a fact that the sum of the forces in X is equal to 0, and the sum of the forces in Y is equal to 0. Torque is not in this problem. Ignore it for now. When you're looking at the force diagram of this thing, there are 4 forces. There is T1Y, there is T1X, there is FG down, and then there is T2 to the right. So when you write your force equations, you look at this diagram and you say 0 equals T2 minus T1X. And for the sum of the forces in Y, it's 0 equals T1Y minus FG, which is mg. We'll put that in a little bit. All right. What we need to do is we need to study T1 for a moment. And T1 is this. T1 can be broken into 2 component vectors. T1y, or not, yeah, component vectors. T1y and T1x. Now this particular angle was given, which is 30 degrees. So what I know is that sine of theta, which is opposite over hypotenuse, is T1y over T1. So T1y is equal to T1 sine of theta. And I know cosine of theta is adjacent over hypotenuse, which is T1x over T1. So T1x is equal to T1 cosine theta. So on this next line, 0 equals T2 minus T1 cosine theta. And 0 equals T1y, T1 sine theta minus mg. And what we do is we look at these particular problems, and that the only unknowns we have are the 2 tensions, which means the equation on the right only has 1 unknown. The equation on the left has 2 unknowns. So solve for it. mg T1 sine theta. So T1 is mg over sine theta. And the reason, well, dang it, you got g is the dumb 9.8. Hold on. M is 20, g is 9.8, and then you got the sine of 30. And I love the sine of 30 because it is 0.5, so it is 40 times 9.8, or 392 newtons. Now that T1 is known, we can solve for T2. T1 cosine theta is T2. So T2 is T1 392 cosine of 30. $339.5. And that is the solution for that. It is a simple translational equilibrium. It illustrates the idea that the forces in the horizontal and the vertical add up. Yes. Those 2 equations, and I'm about to introduce the other one, are your best friends when doing this equilibrium problem. Okay. So the next one, let's see, what am I going to do? I'm going to do this one. Okay. This is what I would call a torque bar problem. A torque bar problem, when you see something like this, you should have just an immediate instinct to write these two equations. Sum of the torques is equal to 0. That's your first friend. Your second friend is the sum of the forces vertically is equal to 0. The bar is not rotating. The bar is not in translational motion. It's not moving up, down, left, right, forward, back. Forward, back, left, right are boring, but the vertical forces are the interesting ones. This one, you've got to sum the torques first. You can't do the sum of the forces vertically is equal to 0 because you don't know F and you don't know T, so you're kind of hosed that way. But what you do is you remember that crazy little top hat image that he drew, and he asked you, like, it looked like, I was very happy that there were people last night who just went, I know that one, I just hate that. It looked like this. He had arrows all over the place, and he said, pick the point that's the wisest, basically. And you've got to pick a point that eliminates one of the forces that are unknown. We've got two choices. It could be either that one or that one. You're allowed to pick which one you want. For me, I tend to pick the furthest one to the left. Why? I don't know. But either one would work. So I'm going to pick A. So the sum of the torques about A is equal to 0. Now, there is a torque from F, but F times 0 is 0, so I don't really write that down. I don't really care about that force at that point. But 0 equals, I've got that force down, and that tension up. So I'm going to write M1G, M2G, and tension. Then torque is the force times the distance from the rotation point, which in this case is A, to the force. So the distance for M1G is x1. The distance to M2G is x2, from there to there. And then the distance from there to T is x2 plus x3. Now comes the application of the signs. And last night, I made an attempt to teach you guys the right-hand rule. Whoop. Oh, yeah. Thank you. I've got an autofocus button. All right, I don't know what it does that sometimes. I really need a TV that just looks back at that, and then I can see what I'm doing. And thank you. That's exactly what you guys should have done. The way that I do this is that torque as a vector is F, no, not F, R cross F. So what I typically do is I go from there and I point in the direction of the force, down, up, or positive. So that one is positive. If I go from there to the right, I'm going to show you an easier way. But last night, for the people who saw this, that down into the page is negative, and then there, up, out is positive. So those are the signs. The other way that I could do this, and for a lot of people you're immediately going, oh my goodness, what is he talking about? What I would do to simplify things, this is the simpler way, is that if the force would cause, or if the torque would cause a rotation counterclockwise, it's positive. So that force pulls this over counterclockwise. That force pulls it over counterclockwise, so those are two positive. If it is clockwise, it's negative. Let me get that. I think that is messing it up. You can use the right-hand rule. I do that. And what's really weird is people have seen him do it, but he hasn't explained it as to why is the sign positive or negative. He just does this weird thing with his right hand. That's the right-hand rule.
He like mentions the counterclockwise when he talks, but he goes, oh, it's counterclockwise, and then it talks, and it's
Yeah.
like, okay.
There's a yeah, it's a machine. To the people who will spend 2 minutes working on this. The right-hand rule, I taught my 8-year-old niece to do the hand gesture. This, that, and that. The first vector, palm, fingers, and forearm all point in the same direction. So from A out to M1G is that way. The second vector is the force vector. You want to curl your fingers in that direction. So F, fingers curl down towards the page. The third vector is how my thumb points. See how it's pointing naturally away from the whiteboard? That's out of the page with palm. Excuse me? What I'm saying is I'm not looking at F, I'm looking at M1G. Yeah. I'm looking at those forces. So for the tension, from A to the tension is to the right. The tension is up. Thumb points out of the page for palm. Now, the one on the right for M2, that one from A to the force is to the right. The force is down. Thumb points into the page, or negative. Now, how I do it, because I've done it so many times, for M2G, I would just go negative. Because I did 1, 2, 3 in very quick succession. I've been working on teaching my niece the right-hand rule since she was 2. She was in the no phase from 2 to 5, so that was a little difficult. But 8 got her to do the motion. I'm really trying to figure out when this is going to happen. But in my class, we spend a half an hour working on this. So the night before the test is not a good time to get the subtle points of this. But now that we've determined the signs, we can start cranking through this. I'm looking for T. I'm going to divide by this and factor G out of the top. The hardest part of this whole thing is to just get the torque problem set up and get a number. Once you got this, that's trivial. So this is 60 minus 2, 58 times 9.8 divided by 4. I get 142.1. Now you could sum the torques around the other point just to get F. Sum the torques around B to get F. But that, in my opinion, is a waste of time because you've got your friend translational equilibrium just sitting there waiting. So what I would do is this. Yes. I've had advisors go, Eschenberg. Oh wait, never mind.
Well, no, it's just like, I thought,
What'd you think?
for exponential slope forms that you didn't remember out the math exponential.
Correct. So f plus t minus m1g minus m2g. So m1g plus m2g is equal to f. Well, oh wait, let me put that over. Minus t is equal to f. So those three terms came over. So this is 1 times 9.8 plus 20 times 9.8 minus 142.1, and that is equal to f. And I get 63.7 Newton. And so that's the answer for that. So when you do stuff like that, it is the that's the kind of attack plan. Now what I'm going to do, the setup of this, just so you know, is similar. I had talked about problem 9, chapter 9. The setup is like that. It's a, yeah, okay.
I'll see how I have right now.
Mhm. This is similar to the setup of problem 9, chapter 9.
And this one requires tension. The one in chapter 9 is the one where like the piano is 1/4
Yeah.
inside. Yeah.
And they never give you the length of the piano or the length of the bar.
All you have to do is just do 1/2, so it gets you to the
Yeah.
simple
We're kind of trying to think about problems that I think this is useful, and but what I think is going to be more useful is something like this. For those of you who are taking exercise science and plan on taking biomechanics in the spring, this guy is going to be your not your best friend, your worst enemy. You're going to see stuff like this all the time. This is equivalent to, now granted, this is not to scale to an actual human arm, but this is the elbow, that's the hand and the mass of the arm. This is the muscle holding up the arm. So the question is, given these conditions, what's the tension in the muscle? It's not what? It's not moving. Yay, not moving. Which means that the sum of the torques is equal to 0. Now, there is, when you look at last night, I'll post it tonight, the videos, or at least hopefully if I remain conscious. Problem 19, chapter 9, for B, the vertical and horizontal components of the force exerted by the pivot point A. I don't think that he's going to ask a problem like that because it would just take too long. He only has 75 minutes. If it was a 3-hour celebration, you may call it a final. I mean, it could be on it, but it would have to be the only problem that he does. Problem 19, page 253.
That one about the stoplight?
Yeah, the stoplight with the weird bar.
Yeah.
That one's a fun one.
Yeah, we're doing that.
I don't think that he would put it on the test because it's just mean and it's too long. And it's mean because it's too long. I think stuff like this is legitimate. Yeah. 15 minutes per problem? Okay. Now, for a problem like this, the sum of the torques is equal to 0. Yay, no rotation. Which means that we need to take a look at how the forces break down. That is Ty. That is Tx. And that is the force of gravity from that mass. We've got to choose a sane rotation point, and there's only one worth noting, and that is that guy right there. The pivot point is the hinge, what it is right now. With this, Tx is aimed directly at the hinge. Tx makes no contribution to it rotating. If you look at a door, if you stood at the door and you pushed on the door right at the hinge, that door is not going to open or close. It won't have, your force will not have any effect on it. And that's because since it's aimed at the rotation point, its distance is 0 in terms of the side-by-side distance. So what we have here is that the sum of the torques is equal to 0, and the two forces are Ty and Fg. Well, what are the distances? The distances are x1 and x1 plus x2. Well, let's do the signs. Well, the right-hand rule, or the fact that that force would make it counterclockwise, makes that negative. Or, I'm sorry, positive. It does, yeah, in the end, it doesn't really matter as long as those are opposite signs. Because that one causes it to rotate clockwise, which is into the page, or negative. So I am looking for, well, what am I looking for? I'm looking for T, and I only have Ty. Well, let's look at some geometry, or trig. No, let's not look at geometry. The most scathing review that I ever got, she hated me, or he, or I don't know who it was. But in the middle of this just insane rant, she goes, all physics is applied algebra. And I was like, yeah, I don't have any problem with that. That's kind of what I've been saying for years. Applied algebra and applied trig. Think of this as algebra 3, where it's just different systems and you have to identify how the equations work together. This Ty and Tx can be rewritten like this. And that length is x1 and that length is y. And what ends up happening is that angle there, or theta, is that angle there, or theta. It could be that one and that one, but either one is fine. So tangent of theta is opposite over adjacent, which is y over x1. So theta is the inverse tan of y over x1. Inverse tan of 1.8 over 1.2. And that gives me 56.3. And because that theta and that theta are the same, and that is t, the sine of theta, which is opposite over hypotenuse, is ty over t. So ty is t sine theta. Plug that into here. 0 equals x1 t sine theta minus mg, because force of gravity is mg, x1 plus x2 and I'm left with mg x1 plus x2 x1 t sine theta. So t is mg x1 plus x2 over x1 sine theta. M is 100, 9.8, x1 is 1.2, 2.4, x1 1.2, sine of 56.3. And I get 9,800, or yeah, God, I can't think right now. So the tension in the cable is 33.8 Newton. And so that's the tension in the cable. Good, and we're on track, we're on schedule. Yes? A lot of times, if he gives you the dimensions only, you're going to have to find theta. Unless he gives you theta, and then that's just great. But you would have to find theta. So quite frequently, when I'm doing problems like this and I see a bunch of lengths, tan theta is usually on my speed dial, ready to go. All right. So what we've done now is we've done chapters 8 and 9. We're going to move on to 10, and 10 is the big guy. And so what I have done is I've made 4 problems, and what I'm going to do is rank these from beginning to end. So you have 50,000 kilograms of material. It's 4,000 kilograms per cubic meter is its density. It's in the shape of a cube. What is the total pressure on its base? Let me introduce you to the most useful equation that you will ever need in chapter 10. And that is that the density is mass over volume. I call that, all right, see you guys later. You're very welcome. I call that the Swiss Army knife equation. And why is that? It's because whenever I'm dealing with chapter 10 material and things just look weird, I throw in this or that or that into the mix. And it typically, if I don't understand either density, mass, or volume, I substitute it out using that. Now, pressure is force over area. The force is the mass times the gravity. The area is, well, I'm not so sure. But I do know that density is mass over volume. So volume is mass over density. And then, what am I looking for? Oh, and then I know that also, because it's a cube, and this is the way that I wrote it, volume is L cubed. So L is the cubic root of volume. So L is the cubic root of m over rho. And so m is 50,000, rho is 4,000. I take the cubic root of that, and then I get hold on. I get a length of 2.32 meters. So area is L squared. So the mass is 50,000. The gravity is 9.8. And L squared is 2.32 squared. Now, one of the things that I'm going to show is that the pressure due to the cube is 91,037 newtons per meter squared. There's another way that you can solve this, that the pressure due to a material is the density of the material, the gravity, and then the height. The density is 4,000. There's a proof for this, but either way is correct. And what we get is, just to double check and make sure, well, it's close because there was probably a rounding error somewhere over here. It's 90,000 and 944. Close enough in terms of what you guys are doing. This equation here you can get from that equation there. Excuse me? This? How did I get it? If you've got a cube of material, length times base times height, it's L cubed, because in a cube all sides are the same. Okay. Now it could have been I could have made it a cylinder, I could have made it a rectangular cube, or rectangular solid. There's all sorts of geometries. But the thing that I wanted to show this is how you could do it this way or you could do it that way. Just find the height of the material will give you the pressure. Now the thing that you have to remember is that 1 atmosphere is 1.013 times 10 to the 5th newtons per meter squared. And that gives me 0.9 atmospheres. That's the pressure of the object on the ground. But that's not the total pressure. Remember, with gauge pressure, it's whatever you read on the gauge plus 1 atmosphere, because you've got all that atmosphere on the outside of the tire, that the pressure is, in addition to it being up, there's an extra atmosphere. So P total is that pressure plus the pressure of the atmosphere. So 0.9 plus 1 is 1.9 atmosphere. Because I did not ask for the pressure of the cube, I asked for the total pressure on its base. And so you've got to remember to have that extra 1. It depends on what he asks. If he had said, give me the answer in newtons per meter squared, or pascals, which is equivalent, then all I would do is I would go 9944 plus 1.013 times 10 to the 5th, and add that up. It all depends on what he's asking for. All right, the next is a buoyancy problem. The buoyancy problem is I thought I'd change things up a bit. Rather than have an object under the water, I'd have an object in air. And this air is filled, or the cube is filled with, not cube, sphere, filled with helium. The densities that we need to know is that the density of air is 1.29, and that's kilograms per cubic meter. You're very welcome. And that the density of helium is 0.179 kilograms per cubic meter. The tension in the string holding the balloon down is 50 newtons. Now, one of the problems that writing problems like this is fun is that I haven't done the math. I understand how the equations work. So what I'm going to do is, if the math doesn't work because I chose the wrong numbers, I'm going to change the numbers to make them work. But the physics remains the same. In this, you've got the buoyant force up, you've got the tension down, and you've got the force of gravity pulling down as well. That shell and the helium are both pulling down because they have mass. Well, what do we know? This thing isn't moving. Yay, not moving. So the sum of the forces vertically is equal to 0. Well, 0 equals buoyant force minus the force of gravity minus tension is equal to 0. The buoyant force is rho Vg. That rho there is the density of the fluid being displaced, so it has to be air. The volume is of the balloon, gravity is gravity. The force of gravity is the mass of helium plus the mass of the shell times gravity. The helium does have mass, and so you're going to have to measure that. And then the tension is T, and that's given. So the goal of this algebra problem is to discover that thing right there. So we're going to have to solve for it. So mass of helium plus mass of the shell times gravity is equal to rho A Vg minus T. Divide both sides by G. Mass of the helium, mass of the shell, rho A V minus T over G. When you divide both sides by G, that G will cancel. That T will be divided by G, and you get that. So the mass of the shell is the density of air times volume minus tension divided by gravity minus the mass of helium. Well, we don't have the mass of helium, but what we do have is the Swiss Army knife. The density of helium is the mass of helium divided by volume. So the mass of helium is equal to the density of helium times volume. So this becomes density of air, volume, minus T over G, minus the density of helium times volume. So this is 1.29. Volume is 500 minus 50 divided by 9.8 minus 0.179 times 500. Oh wow, it's going to work out. All right, great. Always helps when the math works. Times 500. And I get a mass of the shell is 550.4 kilograms. So the core of this problem is being able to identify the forces, how they add up, understanding what the buoyant force is, understanding how to work what the Swiss Army knife equation is, and yeah, so that's it for that one. Okay. Now, one of the things that I've seen on a regular basis is the whole idea of apparent mass and true mass. True mass is m. That's the actual mass of the object. And then there is apparent mass, the apparent mass is the normal force divided by gravity.
Okay,
Yep.
and,
Oh, on the previous problem? 550.4.
okay, thank you.
So the apparent mass is the normal force divided by gravity. The true mass is mass. Now I gave you that the apparent mass is 2 kilograms, but its true mass is 7. I give you the volume of the mass itself, and I want to know the density of the fluid around it, the density of the fluid that it's displacing. Now, it's resting at the bottom, which means yay, no movement. So the sum of the forces vertically is equal to 0. When you do the force diagram on this thing, you've got the buoyant force up, you've got the normal force up, and then you've got the force of gravity down. So the normal force is up, the buoyant force is up, and the gravity force is down. Well, the normal force, what I'm going to do is I'm going to divide everything by g. So 0 divided by g is 0, normal force divided by g, buoyant force divided by g, and the force of gravity divided by g. That's a subscript, so it's not going to cancel anything. And that gives me its apparent mass. The buoyant force is rho of the fluid being displaced, so rho sub F, and I'm going to be looking for this. The volume of displacement, and then G, and then divided by G, and now those two G's cancel. The force of gravity is its true mass times gravity divided by G, and those G's cancel. Now what I'm looking for is the density of the fluid being displaced. So M minus AM is equal to the density of the fluid times volume. And then, okay, I did give its volume. So the density of the fluid is M minus apparent mass, that M is not that M, divided by volume. So the mass is 7, the apparent mass is 2, the total volume is 5. Ooh, I love this. So the density of the fluid is 1 kilogram, or the density of the fluid is 1 kilogram per cubic meter. And so that's how you find it. It's all playing games with buoyant forces and translational equilibrium. That guy and that guide. And then usage of no, I didn't need the Swiss Army was not useful in this one. Yes.
Is the reason that the normal course is a fair amount, is that because of the skating fields?
I gave you a